Okay, so just to correct an error last time, this is always the danger of doing calculations in real time on the blackboard. I made a very silly mistake. I just transcribed this thing wrongly. So when you get to the point in your notes where we write out the Riemann tensor, remember we say that G equals eta plus H. We had some formula that the Riemann tensor goes like G with two derivatives. And just transcribing it, I put the wrong indices here. So if you literally just take the formula for G, plug this in, keep the indices straight, this rho sigma mu nu will go like rho how does it go? I've forgotten. What's the order of the indices in that formula? First, last, second, third. 1/2. First, last, second, third. No? Okay, so we had some formula like this, and just plug G equals eta plus H, you'll get the right formula here, and then everything else is fine. Okay, so I simply transcribed two indices wrongly on the left. So the way we calculate R00 is a contraction of the Riemann tensor, one raised, one lowered, and then the point is we look at this formula, and anything involving time derivatives is 0 by assumption. Okay, so we want two zeros in the Riemann tensor. Raising and lowering, we just do with eta, because this is of order h already. So if we took into account the h in the inverse metric, we'd be getting a higher order in h. So just raise and lower with eta. And so you just have to keep track of the minus sign in the eta. So 0, 0 means the second and the fourth index are 0. And so in this formula, this is the correct formula. Okay, so the correct formula means nu and rho are both 0. So the only term which is non-zero is this guy, because it's got zeros here. Okay, everything else has 0 in a derivative, and therefore it's 0. Okay, so you get minus from this term, and then you're contracting these two indices with an eta, and the only non-zero term are spatial derivatives. Those are not 0, and this is just delta ij in the spatial direction, so I get, there should be a half here. So I get minus a half del squared h naught naught, right? And everything else was correct, so there was just that minus sign. And then we had rewritten the Einstein equations, so this was kappa t naught naught minus 1/2 g naught naught t lambda lambda, and this thing gave us kappa times rho c squared minus 1/2 rho c squared. And we'd already seen earlier that h naught naught was equal to minus 2 phi over c squared, where phi is the Newtonian potential, Newtonian gravitational potential. Okay, we did that from the geodesic equation, comparing it with F equals ma for gravity. And we also have del squared phi equals 4 pi g rho, where from Laplace. So plugging this into here, the minus 2 cancels the minus a half. I just get del squared phi over c squared. Del squared phi over c squared is 4 pi g rho over c squared. And equating the two sides, this is kappa over 2 rho c squared. Equating the two sides, we get kappa equals kappa equals 8 pi g over c to the fourth. And so we infer the Einstein equations. G alpha beta is 8 pi g over c to the fourth T alpha beta. Yep.
About the rigid tensor, like the R00, are you missing an eta mu rho in the second? Well, it should be rho.
Oh, sorry. This should be mu mu. Yeah, if I contract a raised and a lowered, that's equal to eta mu rho R0. R. I wanted the. Yeah, let's put them both down. Okay, so mu 0, rho 0, exactly. Mu rho. Okay, this is, of course, up to order h squared because the inverse metric isn't exactly eta, but I can use eta as long as I'm only working to order h squared. Thank you. Okay, so apologies for that, that mistake. I shouldn't have written on that, should I? Never mind. It's gone now. My mistake is gone. No evidence. All evidence is erased. Okay, let me, I'll leave it there just for a little bit, just so that you can, middle. Okay. Right, so this time we're going to do something exciting, which is the most amazing application of these equations. You know, the way Einstein figured out these equations was inspired guesswork, but all he's really used is Newtonian gravity. Hasn't even used any information about the solar system, right? It's literally just something falling on Earth. G is Newton's constant. Speed of light went into it. And that was it. Otherwise, it's just kind of pure logic. And this assumption that curved space-time accounts for gravity. Einstein didn't imagine that this would describe the whole universe. Okay, that seems like a completely absurd extrapolation. But it turns out it does, and it describes it to amazing precision. Right? Literally that equation without amendment. So this is the most amazing extrapolation in science, that we literally just take the Einstein equations and bingo, they describe the whole universe. In fact, the universe seems to be simpler on large scales than it is on medium scales, like the scales we live in. The universe seems to be very simple on very tiny scales, scales of the Higgs boson and particle physics, and very simple on the larger scales, and it's complicated in between. So in cosmology, we want to use GR to describe the whole universe. Let's say the whole observable universe. And we'll see it does amazingly well. And in fact, when Einstein first attempted to see what his equations did for the universe, he got it wrong a few times. He assumed funny boundary conditions for the metric because he wanted to describe a static universe. Nobody even knew the universe was expanding at that point. So he got it wrong a few times, and then he introduced, guess what, dark energy, because dark energy is a very, very natural thing to include in this equation. Remember, the logic of putting this tensor here was that Einstein knew that from ordinary physics that this is conserved, meaning the covariant derivative of T alpha beta equals 0. And this gives the conservation law of energy density and momentum density. And so you had to put some tensor here, which satisfies this equation in order for this to be consistent. But you could easily add to this equation plus some constant times G alpha beta, and it would still be fine. And so Einstein tried that in 1917 and managed to make a static universe model. But in fact, that model fell apart very quickly because it was unstable, as I will show you later in this lecture. But nevertheless, that constant survived, and in like 80 years later, in the late 1990s, this was actually discovered. The dark energy was discovered, and it seems to be described extremely well just by a constant. So it's another example of the amazing power of extrapolation of good mathematical and theoretical principles to the whole universe. They work unreasonably well. It's just mind-blowing. Okay, so let's study solutions to the field equations. Field equations of general relativity are these equations: 8 pi g over c squared T alpha beta, including matter and possible, well, let's just say, and time dependence. Okay, so initially Einstein actually looked for static solutions because he didn't imagine that the whole universe was changing. That seemed a crazy idea. So he tried to look for static solutions. There are special cases of time-dependent solutions which happen to be stationary. But we're going to include time dependence, and then we'll see how the static solutions are just special cases. Yeah.
One thing, in the last lecture, we just reduced this constant with
right.
Proportionality, right? But then you're saying that I can add a constant times the metric. Right?
There are different ways. Yeah, there are different ways of looking at it. The modern viewpoint is really just to absorb this into the T.
Okay, because I mean, if I do it from the beginning, there's no way I can fix that constant T from a classical point of view.
No, and we still don't know how to fix C.
Okay.
C is an arbitrary constant, and it's still an arbitrary constant. What we are actually searching for in physics is a fundamental principle which will fix the value of C. Because C takes a crazy value. C takes a value of 1 millielectron volt to the 4th power in particle physics units. Or in Planck units, C takes the value of 10 to the minus 120 Planck mass to the 4th. And this is the biggest mystery in quantum field theory. Nobody knows how C can be so small. You can add up the vacuum energy in the bosons and the fermions. It's not 0. The fermions actually win in the standard model because there are more fermions. And they give a negative contribution to this number of minus m Planck to the 4th. So that's quantum field theory treated naively. I mean, it just literally says that the cosmological constant is negative, huge number. And we don't know how to fix that. We have some ideas, okay? I've got some ideas. But people are struggling with that problem. And at the moment, no one really knows. And I think in my welcome to you, I said this is one of the things that has motivated this notion of a multiverse, that maybe C is a random number. and that there are actually trillions of possible universes, and each one would have a different C, and we just happen to be in the one where C is small. And that seems to me the most extravagant hypothesis you could possibly make, and it's not very satisfying. And I think it really fails to live up to what Einstein and Maxwell and others did, which is to simplify the description of nature rather than complicate it. Okay? So I view that as an embarrassment. The multiverse. Multiverse is nothing but an embarrassment. Okay. So we want to include time dependence. And to simplify the equations, you see, these are very complicated equations, right? The most general solution of this equation, what is it? It's a set of partial differential equations in space and time, nonlinear, for 10 quantities, g, alpha, beta, of time and space, right? These are 10 equations for the g, alpha, beta. And it's a hopeless task to classify the general solution. I mean, these equations describe lumpy universes, crazy universes, black holes, you name it. So it's a hopelessly difficult task to analyze the most general such solution. But we can study a subset of solutions by imposing symmetry. Impose symmetry. And the symmetry, so at this point, we don't really know why we're justified in imposing this symmetry. The equations don't impose any symmetry. But the universe is extremely symmetrical, okay? So what physicists do when we don't quite know what to do is we look at the answer, which is the universe. And we say, well, the universe looks pretty symmetrical, right? It looks almost the same in all directions. So let's assume that for some reason it has to be that way. And we have to come back later and try to justify that assumption. It's a very big assumption. So the symmetry we'll impose is maximal symmetry in space. Okay, so maximal symmetry, so we look around us, we see a universe that seems to be pretty much the same in all directions, on average. Okay, the density of galaxies on one part of the sky and the other part of the sky are very similar. The temperature of the microwave background is very similar. So that imposes, that is isotropy. It looks the same in different directions from one point, when viewed from one point. But more than that, it looks like we don't live in a special point in the universe. All points look the same. And that's a statement of homogeneity, that if I translate my position around the universe, nothing changes. And if I look in different directions, nothing changes. So these are homogeneity and isotropy. And this idea of imposing symmetry on the universe was due to Einstein, and it was called the cosmological principle. Just there's no real principle behind it. It's just cheating. Okay, look at the answer. Now, actually, Einstein didn't cheat, right? Because Einstein didn't know the answer. Einstein just said, look, these equations are too complicated. So let me simplify by restricting to symmetrical universes. Just completely reasonable if you don't know any better. So in d dimensions, actually, let's call it little d. So the idea of the cosmological principle was to say that the spatial part of the metric is maximally symmetric. No point is different than any other, and no direction is different than any other. In d dimensions, the greatest number of possible symmetries of a manifold with a metric is d plus 1 over 2. Okay, so in d equals 3, there are 6 symmetries. Okay, and you can think about these as being the 3 translations in space and 3 rotations, right? A rotation is rotation is defined by picking an axis and rotating around it, and there are 3 independent axes of rotation. So, oh, I've done it again. I'm sorry. Now I'll move over here. So the spaces with maximal symmetry in 3 dimensions, yeah.
2 questions. First of all, this assumption that the universe should be entirely homogeneous and you should
Isotropic.
It should be isotropic. Does that not imply that you should have a universe with no boundary as such?
No, it doesn't imply. It's not you. The differential geometry. So technically, symmetry means isometry. Okay. You've studied isometries in the example classes. So an isometry is defined by a local equation, okay? And the metric is a local concept. It has nothing to do with the topology of the space. The topology is the question of whether it has a boundary or what the global properties are. So when you say symmetry, it doesn't imply anything about the global properties. So you can have geometries which are compact in a topological sense, meaning they are finite. For example, a sphere is the obvious one. Okay, but if the space is positively curved, if the Ricci scalar is positive of the 3 space, that will be a sphere. The space of greater symmetry is a sphere. If the Ricci scalar is 0, that'll be flat space. But you can have a torus. You can say I've got a box with periodic boundary conditions, so that when I travel out one side of the box, I come in the other. And that's defining the topology of the space. And that's a torus, but it's compact. Or even if the Ricci scalar is negative, you have a negatively curved space, and you can have compact negatively curved spaces, which similarly have an identification of boundaries. So the topology has nothing to do with the local symmetry or differential geometry of the space. It's a separate assumption. So I'm not going to be saying anything about topology. It's a big question. If the universe has a trivial topology, just continues forever, or if it has some identification of boundaries. You know, if I travel that way in the universe for a long time, am I going to come back from this side? We don't know. Simplest assumption would be, well, it's subjective, but let's just say we don't know at this point.
How do you get that equation, like in
the dd plus 1 over 2? Yeah. It's a long proof. You will find it, for example, in Steven Weinberg's Gravitation and Cosmology. He proves it. But the place you prove it from is the Killing equation. You just take the Killing equation. Killing equation is psi mu colon nu plus psi nu colon mu. This is enough to define an isometry of the metric. And what you prove is that in d dimensions, there are only the maximal number of solutions of this equation is 6. Is dd plus 1 over 2. But in 3 dimensions, it would be 6. Okay, so I'm just going to take that as given. It's pretty obvious what the solutions are. In d equals 3, we get a 3-sphere. Okay, so 3-sphere looks pretty symmetrical. And indeed, it has 6 rotations. Okay, you can think of a 3-sphere as just the solution to this equation equals 1 in 4-dimensional Euclidean space. And then you just ask, well, what are the rotations in 4-dimensional Euclidean space? Right? Well, the rotations are things like x dy minus y dx. Right? That's a rotation. And in 4 dimensions, there are 6 independent quantities like that, 6 independent rotations, and they just rotate the sphere around. Or you could think about this as antisymmetric matrices. X prime equals OX. This is a 4x4 matrix. The generators are antisymmetric 4x4 matrices, so there are 6 of them. The second obvious solution with 6 symmetries is 3-dimensional Euclidean space, just flat space. And this has 3 rotations and 3 translations. And the third one is hyperbolic 3-dimensional space. And this one has 3 boosts and 3 rotations. And so the way you construct a hyperbolic 3 space is you consider the equation t squared minus x squared minus y squared minus z squared equals 1. It looks like this. In 4-dimensional Minkowski space, so t goes like this. X, y, z are spatial. And then the hyperboloid looks like that. There's another branch of the hyperboloid here, disconnected, but you just take one of these. And within this Minkowski space, I can do 3 ordinary rotations, or I can do 3 transformations linking t with x. And those are Lorentz transformations in 4-dimensional Minkowski space. And they're guaranteed to leave you on the hyperboloid. So they are isometries of the hyperboloid. Okay, so that's all there is in 3 dimensions. In 3 dimensions, that exhausts the list of spaces with maximal symmetry. And so Einstein's guess was, well, maybe the universe is one of those on large scales. Okay, so we'll see how to construct the metric. Let's do it for S3. For S3, we just use this plus y squared plus z squared plus u squared equals 1 in E4. And so obviously to solve this constraint, I just say x equals sine chi, sine theta cosine phi, y equals sine chi, sine theta sine phi, z equals sine chi cos theta, u equals cos chi. Okay, and then work out the induced metric. So I take the metric on E4, which will automatically possess all of these isometries because the space is so symmetrical. And I just plug these formulae into it, and what you'll find is d chi squared plus sine squared chi d theta squared plus sine squared theta d phi squared. And so that's the metric. That's the metric on S3, which has maximal symmetry, also called the round metric on S3. So we write the line element. We also write this. We commonly by defining R equals sine chi. So one way to think about this is that at fixed chi, I can ask, what is the space that I have? What's a two-dimensional space at fixed chi? And this is obviously a two-sphere. Okay, so at fixed chi, this is the radius squared of the two-sphere. Okay, so as I think about going out in chi, I have some radius, which is sine chi. This is the radius of S2, constant chi surfaces. And just changing variables in there, we'll see that the line element ds squared is equal to dr squared over 1 minus r squared plus r squared d omega 2 squared. This is the metric on S2. Okay, so often the metric on a sphere is written like this. And this is what you'll see, so here I assumed the S3 had unit radius. If the radius was R0, then we would get ds squared equals, so just by dimensions, you can restore the R0, r squared over R0 squared plus r squared d omega 2 squared. Okay, because r has dimensions of length, and you need the R0 there to make the 1 minus r factor dimensionless. So I'll leave that to you as an exercise if you want to check that. Obviously, what you would do is instead of those formulae right at the top, instead of equals 1, you'd have equals R0 squared. The x, y, z, u would have an R0 in them. And when you go through this calculation, you'll discover there's an R0 over here. Similarly, for so you see the thing that's obvious in these coordinates is that, so obvious that for r much less than R0, for distances much smaller than the radius of the sphere, you can ignore this factor, and then it looks flat. Okay? Looks flat. So similarly, for H3, basically the same formulae, just with replacing some of the trig functions with hyperbolic functions. So we put x equals, because we've got a minus sign in the H3, we'll need to say t equals cosh chi, and x, y, z will be sinh chi, and then sine theta, cos phi, etc. Okay, and if you work that through, you'll find ds squared. So this is now being induced from the Minkowski space metric, in which H3 is embedded. H3 is embedded in Minkowski spacetime, in a Minkowski spacetime. So taking the Minkowski space metric, which would be minus dt squared plus dx squared plus dy squared plus dz squared, we will get d chi squared plus sinh squared chi, d omega 2 squared. And again, defining, defining r to equal sinh chi, okay, just the radius of the two-sphere, then we get dr squared over 1 minus r squared, 1 plus r squared actually in this case, 1 plus r squared plus r squared d omega 2 squared, and that's equal to, and that if we restore, or H3 of radius r0, we get dr squared over 1 plus r over r0 squared plus r squared d omega 2 squared. Okay, so that's defined the spatial metric of the simplest, most symmetrical universes. Let's now discuss the space-time metric. So this will be ds squared, which is g mu nu dx mu dx nu, and that's going to be g naught naught c squared dt squared. And you know what? I'm going to choose c equals 1 from now on. I'm just going to choose units. Okay, so that's just g naught naught dt squared. And then we have 2 g naught I dt dxi. And we have gij dxi dxj. Okay, so that's just writing out the different terms on the left-hand side. So this now we have to decide what to put in here. Now, homogeneity and isotropy in space leads to the following. G naught naught is G naught naught is a function of t and x, but it's supposed to be homogeneous and isotropic, right? A scalar function of space, which is translation invariant and rotation invariant, has to be a constant. So in other words, G naught naught has to only be a function of t. homogeneity in isotropy implies that G0 is only a function of t. And now, actually, you can just remove it by defining dt square root of G0. Let's do it this way. G0 will be negative, and so minus G0 dt squared is going to be defined to be let's just call it dt prime squared. Okay, i.e. dt prime is going to be equal to minus the square root of minus G0 dt. G0 is a function of t, and so I can integrate this. So t prime is just integral. Okay, and if I do that, then the first term just becomes minus dt prime squared. Minus dt prime squared, okay, plus 2g0I dt prime dxi plus gij xi x dxi dxj. So that's often very useful when dealing with a metric to change coordinates in which the metric looks simpler. And in this case, you can, as long as G0 is negative, you can just change coordinates to ones in which the first term is minus 1. Yeah? No. Oh, the second one. Oh, good point. So it won't really matter, but yeah, that's true. It's so let's just call that G0 I prime. Okay, so you're right. When I change from dt to dt prime, I pick up some factor there, but that's just G0 I in the new coordinate system. So we haven't lost anything. Okay, so this includes. And now I'm just going to drop the primes. So drop the prime. Okay, and just this is my new time. Now I have to look at this quantity. G0I, again, it's got to be isotropic. Okay, the assumption is that the metric is isotropic. Now, G0I is a vector, right? Any vector, if you have a space that is isotropic, you can't have a vector. Okay, you cannot have any special direction. G0I, if it was non-zero, would define a special direction. That can't be allowed. And this must be 0 by isotropy. Okay, you simply can't have a vector around if you have an isotropic space. Yep.
I'm under the impression that they're combining the two G0I and GI0 terms. Presuming assuming there that the metric is
symmetric.
Is that always assumed?
Yes.
But has anyone considered the possibility that it's not symmetric?
If it was not, we're always assuming. So G mu is by assumptions is symmetric by assumption. They would be very radical. Remember, the basic assumption is that locally space is flat. And in flat space, you use the Minkowski metric, which is symmetric. So if your metric was antisymmetric, you would somehow have to make sure that the antisymmetric components vanished. Yeah, so I think it would just be incompatible with the idea that space is locally flat to have it antisymmetric.
So in a weak diagonalized necessarily even assume that you look.
Yeah, that's right. It wouldn't be diagonalizable. Yeah, that's true. Or necessarily. Right. Okay, let's not dwell on this too long. So any vector must be 0 by isotropy. That's very important. A tensor doesn't have to be 0 by isotropy. In fact, so this guy is a function of t and x. And this metric, so what is this? Well, this is a spatial metric which depends on t as well as x. Okay, but we know the x dependence has to be one of those three cases. The x dependence has to be one of S3, E3, or H3. There's nothing else that's allowed by maximal symmetry. Okay, and so it follows that Gij of t and x is equal to some function of time, which we'll call a squared, to show that it's positive, times gamma ij of x, where gamma ij of x is the metric on S3, E3, or H3. Okay, so the result of homogeneity and isotropy is that we can always choose coordinates, such that the metric, or the line element, is minus dt squared plus a squared of t, gamma ij, dxi, dxj. Okay? And this is called the Friedman-Robertson-Walker line element. Yep. Because we wanted 3 positive eigenvalues and 1 negative. Right? That was the assumption of the geometry. Locally, space-time is Minkowski space. And I've assumed that the time direction has a negative eigenvalue. So the space has to have 3 positive eigenvalues. Right, so isotropy, homogeneity and isotropy imposes these profound restrictions on the metric. And basically, this quantity A is obviously the scale factor of the universe. Okay, in the case of a 3-sphere, you literally imagine you have a 3-sphere with metric gamma ij, the 3-sphere metric we wrote down, and then A of t just blows it up. Okay, so you can think of A of t as being proportional to the radius of this 3-sphere. And likewise, for the H3 or the E3, all you're doing is blowing up the spatial metric as a function of time. Yeah.
I think the assumption that your space is so homogeneous and isotropic doesn't fix the metric on S3, E3, and H3 to be diagonal.
It fixes it to be the metric on H3 or S3. That's all. You can then choose the coordinates to be these ones, in which it's diagonal. But it's up to you to pick whatever spatial coordinates you like. Okay, the theorem, which I haven't proven, but I've made plausible, is that if you have maximal symmetry, if you have homogeneity and isotropy in space, then the metric then it must be possible to write the metric in this form. There's no further assumption necessary. Now, what about the matter? So we're going to assume the simplest kind of matter, a perfect fluid. And so T mu nu equals, I'll comment on that in a moment, rho plus P u mu u nu plus P g mu nu. And then isotropy, you see the four velocity of the fluid is a vector. But by isotropy, you can't have any spatial components of the vector. Right? There's no vector which is invariant under rotations. So the vector u mu has to be u naught and 0. Cannot have any spatial components. And of course, we must have g naught, g mu nu u mu u nu equals -1. For the fluid has a time-like four velocity, like a massive particle. And because g naught naught is -1, this forces u naught to equal 1. And this is a future pointing time-like vector. Okay, so the four velocity is really easy. And this means that T mu nu takes this form of a rho and then zeros in the off-diagonal pieces, and in the space parts, it's just pressure over A squared times gamma ij. Okay, so in the space-space components, these give nothing. I have pressure, G with upstairs indices. So G with downstairs indices is this matrix, -1 A squared gamma ij. And G with upstairs indices is equal to -1 A to the -2 gamma ij. Where that gamma ij is the inverse metric on S3, E3, or H3. Now, actually, let me just make a comment. Actually, homogeneity plus isotropy force T mu nu to take the form of a perfect fluid. Okay, because isotropy forces the metric to the T0 i's to be 0, and it forces the Tij. Tij is a two-component tensor on this manifold. It is homogeneous and isotropic. The only thing it can possibly be is the metric. And so it forces Tij to be proportional to the metric. And then one can just define whatever functions of time appear here to be the density and the pressure. And that is a perfect fluid. So actually, cosmological symmetry forces the stress energy to take the form of a perfect fluid. This is an example of a statement that, you see, you can't just put any old matter into a universe, right? The geometry of the universe imposes a constraint as to what you can allow. And in the case, you have to satisfy the Einstein equations. And if you impose some symmetry, you have to satisfy the symmetry. And that severely restricts the type of matter you can put into the space-time. Okay? So now we have our equations, the Einstein equations. Okay, G mu nu equals 8 pi G. I put C equals 1, T mu nu. And let's just work out what they are. Let me just see. Yeah.
You choose U0 to be 1.
Yes.
U0 can be -1 as well, right?
Yeah, but I insisted it's future pointing. The 4 velocity, by definition, is a future pointing. For a fluid, it's future pointing. You could say, what's the 4 velocity of a particle? Well, maybe it would say it's going backwards in time, but that's the wrong choice.
Okay, and so you say that isotropy...
It doesn't matter for T mu nu anyway, that's true.
So the velocity has spatial component 0 because we have isotropy, right? So that
Yes.
basically we see our matter to be static in space.
The matter, yes, yes. Another way of saying this is that in coordinates in which the space-time is isotropic, the fluid is not moving with respect to those coordinates. We will call these coordinates x, quote, co-moving coordinates. You can think about the sphere expanding and then the matter as not moving around on the sphere. It's just sitting there while the space expands. It's not going in any direction on the sphere. Okay, so the Einstein equations, well, if we just use G mu nu, we calculate gamma mu nu lambda. Okay, that's an easy exercise, just to plug in G mu nu into the formula for gamma. And then you can calculate the Riemann tensor. Okay, and then you can construct the Ricci tensor. And I'll just give you the result that R00 is equal to minus 3 A double dot over A. It just involves second derivatives of the metric. R0I equals 0. Of course, it has to be by isotropy. And then Rij, again, must involve two derivatives of the metric. It turns out that Rij is just R3, the three-dimensional Ricci curvature, as a function of the three-dimensional metric, Ij. So it's just the Ricci curvature for a sphere, flat space, or hyperbolic space, plus, and then some other second derivative terms, A double dot plus 2A dot squared times gamma ij. And finally, the Ricci scalar is 6. I should say something about this. For space of maximal symmetry, for a space of maximal symmetry, we always have that the Ricci tensor is equal to some constant, which we'll define to be 2k times gamma ij with k a constant. Okay, so that's a completely general result that maximal symmetry implies that the Ricci tensor is proportional to the metric tensor in any coordinate system. And this implies that the Ricci scalar is equal to, yeah, so that's R of 3 and of gamma. And Ricci scalar, three-dimensional Ricci scalar, is this contracted with the gamma, just gives 6K. In 3 dimensions. Okay, so the 4-dimensional Ricci scalar is 6A double dot over A plus A dot over A squared plus K over A squared. Okay, so these are very straightforward calculations, which you should certainly do just to make sure you've understood everything. And this really is the simplest possible metric you can think about. And so G naught naught, which is, of course, equal to R naught naught minus 1/2 G naught naught R. G naught naught is minus 1, R naught naught plus 1/2 R equals to, so R naught naught is minus 3A double dot over A. A half R gives me plus 3A double dot over A. So I just get, those two terms cancel. So I get 3 times A dot over A squared plus K over A squared equals 8 pi G rho. By the way, I should have related K to R naught. In fact, for S3 of radius R naught, K is 1 over R naught squared. And for H3 of radius R naught, K is minus 1 over R naught squared. Okay? So this K is the Ricci scalar, and so basically it represents 2 derivatives of the metric. So it's 1 over a length squared, and the length that's involved is this length, R naught. Yep. Gauss curvature only meaningful if I embed it in something. I'm not embedding it in anything. Okay. Yeah.
If I take, for example, the Friedman-Robertson-Walker line element with A independent of time, right?
Yes.
And I consider on E3, right, then the metric is basically flat.
Yes.
But then I don't see that the Ricci scalar vanished if I take.
Good point. So, sorry, you're worried about here? This one or this one? So let's first do flat space. I should have said this. For E3, right? There's no radius for E3. It's just flat. K equals 0. And you can think about 3D Euclidean space as just the limit of a sphere where R naught goes to infinity. It's a very big sphere. Or a hyperboloid where R naught goes to infinity. They both have the limit that K is 0. Now, if I look at this metric, flat space K is 0. If it's not time dependent, this is 0. Yep. Sorry? Yeah, R naught is a scale factor, so let us just write out that metric, minus dt squared plus a squared of t So remember, the way it comes in is like this. Okay, so that's the Friedman-Robertson-Walker metric. Now, so your question is, how do I fix this number R0? Now, the number R0 is tied up with the definition of what A is, okay? Because imagine I rescaled A. Imagine redefining A, right? A is equal to A twiddle times some constant, right? A twiddle of T. So now I would have an extra A squared here, okay? Now I could absorb the A into the R, right? So then I would define R twiddle equals AR, okay? And now I would define my metric to be A twiddle squared of T, dr twiddle squared, 1 minus A squared R squared over R0 squared, twiddle squared, right? Plus A squared R squared d omega 2 squared. R twiddle, thank you. Okay. And thank you. Thank you. Okay. And now I could pick, you could choose A to be 1 over R0. Right? Nothing wrong with that. A was arbitrary. And so now I have A twiddle squared. Now let me see, have I done this right? Oh, sorry. No. Right, I should have had an A here as well, right? Okay. A is A twiddle. Yes, sorry. I shouldn't have written it there. That's confusing. A is A twiddle A. Okay. Now, okay, so that was right. This shouldn't have been there, right? Am I right? Okay. Yes, that shouldn't have been there. Is R twiddle over A? Fine. So choose A to be 1 over R0, and now I have dr twiddle squared over 1 minus R twiddle squared plus R twiddle squared d omega 2 squared. Okay, so I just rescaled radius. That's all I did. I rescaled the radius, and you notice when I did that, I set R0 to 1. Okay, so in other words, we can set R0, we can set 1 over R0 squared to 1 just by redefining A and R. Okay, so often in books, you will find this equation where K is plus or minus 1 or 0. And you can do that. There's nothing wrong with doing that. You can just choose coordinates so that K is either plus or minus 1 or 0. Doing so is just amounts to redefinition of the scale factor of the universe. Okay, so in a sense, there isn't really a freedom this is not a number which enters. There is a number which enters, and it turns out it's the ratio of this number to terms in the density, which kind of defines the curvature in units, the spatial curvature in units of the density. But at this level, you can redefine things away. We'll come to this in a moment. Okay, so G00, let's see, that's our first equation. Okay, so this is Friedman. This is 1. This was G00 equals T00. And then the second equation is, of course, Gij, which is Rij minus 1/2 a squared gamma ij r. And that is equal to, let's just see it here, Rij, well, this quantity is 2k times gamma ij. And so if we work this out, let's see, the Ricci scalar involves 6k. So we get 2k minus 3k. And it turns out this gives us the following. I'm not going to keep track of the numerical factors. To a double dot plus k equals, and then 8 pi g Tij, and Tij from over there is just p over a squared gamma ij. So let me just put my gamma ij in here. 8 pi g p, it's with lowered indices, a squared gamma ij. And so what we get is that a dot squared plus 2a dot plus k equals, sorry, there was a minus sign here. Minus equals minus 8 pi g p a squared. So that's equation 2. And finally, we can use conservation, covariant conservation of the stress tensor. And so for that, I just have to use my connection calculated from this metric, put it in here. This is, of course, d mu t mu nu plus gamma mu t mu alpha alpha nu plus gamma nu mu beta t mu, or let's call it alpha, mu alpha. Okay. So this leads to the following equation. I'll leave it to you to check. That rho dot is minus 3 a dot over a p plus rho. And that's equation 3. Okay, so the equations we get are 1, 2, and 3. And these are the equations describing the evolution of a Friedmann-Robertson-Walker universe. Friedmann-Robertson-Walker just means maximal spatial symmetry.
Is the pressure unconstrained?
Yes, good, very good question. In these equations, we've said nothing about P and rho, about P and nothing about rho, right? In fact, homogeneity and isotropy just forced there to be some P and some rho, and forced them to be only functions of time. But I've said nothing about their relationship, nor what they're made of, or anything. Now, what you see is from this equation is you cannot specify rho independently of P. If you specify P, then this equation tells you how rho is allowed to change. Okay? But P is completely free. There's no equation for P dot, right? P, so at this level, of the discussion, P of T is a completely arbitrary function. Okay? Rho is not arbitrary because rho's got to satisfy this equation. Now, of course, if you pick a silly pressure, if you pick a pressure that does something crazy, you're going to find from this equation that the density does something crazy too. Like it'll go negative or all kinds of other things. But so far the pressure is arbitrary. Now, in fact, these equations are all related. Can you tell me the relationship between these equations? The first two were the Einstein equations. This equation is covariant stress energy conservation. Are they independent equations? No, right? Because this equation was guaranteed to be correct by the other equations. Okay, so in fact, 3 is implied by 1 and 2. And that's because of the Bianchi identity. Okay, so the Bianchi identity guaranteed that 3 is true. And if you check that, you see calculate rho dot from equation 1. You'll get some A double dots. And then use equation 2 to remove the A double dots. And all you're going to do is get this equation. Yep.
Why do we take it that rho is determined by pressure rather than vice versa?
You can do whatever you like. You can do whatever you like. But you may get crazy results. Okay? So as long as you're consistent with these equations, you can make any assumptions you like. Of course, what we want to say is that we know what P is and we know what rho are. Those are the particles in the standard model. It's radiation. It's stuff we know. Okay, so in practice, we don't want to just put any old junk in here. We want to predict what P and rho are. But the statement here is that P does not satisfy any differential equation. There's no differential equation imposed. There's no evolution imposed on P. There's a million ways of interpreting the Einstein equations. You can say they're differential equations for the scale factor, or you can say they're constraints on the stress energy. Give me some metric, A of t, give me a function A of t, you can say, well, these equations define rho of t and P of t. So they are equations, but you can interpret them in many possible ways, and people often do that. Okay, so let's look at the simplest solutions of these equations. Okay, simplest types of matter, some simple types of rho. Okay, so the simplest possibility is that e.g. rho equals 0. Sorry, P equals 0. So P equals 0 is a form of matter with no pressure at all. This is often called dust. Okay, so the picture is that you have a bunch of particles. This is essentially what cold dark matter is in the universe. You may have heard of this. It's a hypothetical kind of material or comprising particles that don't interact with each other or anything else except through gravity. And so they have no pressure. If you thought about it as a gas with some thermal velocities, then the velocities would be zero. It's like a gas at zero temperature or very small temperature. There's no pressure. And then you see that 3 implies that the density is equal to some, so rho dot of t is minus 3a dot over a rho. And so that implies that d rho over rho is equal to minus 3 dA over A. And so this implies that rho is equal to some constant over A cubed, with Cm a constant. Okay, and that makes sense that you have a certain density of these particles, density rho of these particles, and as the universe expands, the volume grows, and the density just goes down like 1 over the volume. Yeah.
We have this differential equations for A, right, that come from the Einstein equation.
Right.
Is there any possibility to give some initial conditions for those equations?
That's the whole business of cosmology.
Constant in time. I can either put a condition on A to be constant. I mean, if rho is constant in time, then A is constant in time, right?
No. No. If rho is constant, why is A constant? A is not constant.
No, but from equation 3.
If rho is constant, P is minus rho.
That's one solution. Or
Yeah.
I can choose the other solution to be A constant in time.
You'll fail. Okay, let's do that. Let's assume rho is a non-zero constant. Okay, all these games you can play with, and that is the business of cosmology. Okay, so let's do it. Rho is a constant. This is 0. Now, 2 possibilities. A dot is 0, or P equals minus rho. Let's assume A dot equals 0. This is exactly what Einstein did. Okay, exactly what Einstein did. He said A dot is 0. Okay, now you look at the other. Is this consistent? Whoops. A dot is 0. K got to be related to rho. That's called the static Einstein universe, where rho is related to K. Okay? Now, big problem. Look at this equation. This equation, if P is not 0, and A dot is 0, A double dot may be non-zero. So maybe you were static, but well, sorry. Einstein's static universe is the following. We'll do this in detail next time, but it's a good game to play. Okay, let's assume A and A double dot are 0. Fine. So we drop these two. We drop this one. This tells me rho in terms of K. I must have, if rho is positive, K must be positive. I must have a 3-sphere. Okay, so I've got this ball with some density in it. This equation tells me what the pressure is. You see? This equation tells me the pressure. And you'll notice from this equation and that equation, now, yeah, sorry, I hope I haven't made a mistake. Yeah, but I must have a mistake. I must have made a mistake because, okay, let me just understand. Oh, yes. No, no, that's true. So those two equations together imply P is minus 1/3 rho, right? Okay. Right.
Isn't that modular design true for an ideal gas or something like that?
Nope. But it is true if you have a cosmological constant, right? So for cosmological, we'll do this next time. Cosmological constant, P equals minus rho. Okay? For dust, P equals 0. If you have both, you can arrange that P is minus 1/3 rho. And that is the Einstein static universe. Okay. Sure. Yeah, because you've got a bit of negative pressure. You don't want minus rho, but you want minus 1/3 rho. And that's the Einstein static universe. He has matter attracting itself, the lambda pushing you outwards, and the result balances.
So, okay, so let's assume that has sense.
Mm-hmm.
That P is minus 1/3 of rho, then my Ricci scalar is just K over A squared, right? If A is A dot and A double dot.
The 3-dimensional or 4-dimensional Ricci scalar, right? 4-dimensional. This one from here is 6K over A squared.
Okay, so it will be 6K over A squared.
Yep.
Now, doesn't the initial condition that I imposed over A determines if my Ricci scalar is 0 or not 0?
No, because, okay, you're forced to have a certain value of, let's see it from here. Everything is related, right? So depending on your total density of matter, the curvature is fixed. You see, in a way, so this was all a little bit confusing, but if you construct a quantity which is really meaningful, the curvature of 3D space, okay, this is our, well, you can think about it, let me just, yeah. I mean, R, you see the 4-dimensional Ricci scalar, the thing you know about it, it's independent of coordinates, right? So whatever coordinates I pick, whatever rescaling I do, it won't change this. All right, so that's really the physical quantity, is K over A squared. So R4 is 6K over A squared, and this is like the inverse curvature radius. Squared. Okay, so one way to think about this, if I have a sphere, is the radius of that sphere is really R squared equals A squared R naught squared. If K equals 1 over R naught squared, right? Remember, K is 1 over R naught squared. So you literally picture the universe, that's going to be its radius. Okay, so from this equation, you will see that the radius of the 3-sphere, this is 1 over the radius squared, will be this quantity. We'll get an equation for the size, literally for the size of the universe.
Okay, so the thing is that I have the Einstein equations, they determine my metric, right?
Yes.
And my metric is determined up to this sort of A of T
Yes.
factor.
Yes.
Right? The K is something that you impose as an answer to whether you are in a
Sphere,
space,
exactly,
sphere,
or hyperbolic or flat. Right.
So what I'm saying is that, I mean, this answer is something you put by hand. This is nothing that the Einstein equations throw you.
It's an assumption of symmetry. Okay. So when you make an ansatz for a differential equation, in general, it's just going to be inconsistent, right? It, in general, may not work. You make some ansatz, you find it doesn't work. But if you can make an ansatz with symmetry as your principle, where all you're doing is imposing a symmetry, then you're not, then, let's see, how should I say? That is a consistent way to restrict the possible solutions of the equation. You, yeah, I don't know another way of saying it. basically the only assumption in the ansatz, you left K as free, okay, and the assumption of the ansatz was the symmetry.
So I cannot break that assumption of whether I'm in S3, the hyperboloid, or the Euclidean space by imposing initial conditions on A of t?
No, these equations assume the ansatz, so you better not use those equations if you don't make this ansatz. I mean, I made the ansatz to simplify the equations. I cannot now abandon that ansatz. I mean, that ansatz is built into this, right? So these equations only describe a perfectly homogeneous isotropic universe. That's all they describe, okay? We haven't made any other assumptions other than that, okay, in order to get these. Well, we assumed the Einstein equations, of course, but then we assumed homogeneity and isotropy. That's it. Yeah.
How should we interpret something with negative pressure?
With negative pressure? Okay, so this is weird, this cosmological constant. It has negative pressure. Let me show you where it comes from. You see, if you look at, for a cosmological constant, T mu nu is equal to, let's just do Minkowski space to be really simple, to forget about A's and things, in Minkowski, right? So T mu nu, if you're in the rest frame of the fluid, is rho P, P delta Ij, okay, 0. That's just the definition of rho and P. The rho is the T00 component of a stress tensor, and P is the Tij component if the stress tensor is isotropic, in a frame in which it's isotropic. It's the definition of pressure. Now, for lambda, for a cosmological constant, the defining property of a cosmological constant is that it's Lorentz invariant. Okay? See, ordinary matter, you know, if I throw this at you, it has more energy. So T mu nu is different in different frames for ordinary matter. For a cosmological constant, it's the vacuum, right? The definition of that type of matter is that it's Lorentz invariant. It doesn't matter how fast you travel, it will look exactly the same. And that means it must be a constant times eta mu nu. That's the only invariant symmetric tensor under Lorentz transformations. This is the only possibility. But eta mu nu is C delta Ij. Okay, so from this equation, it follows that P equals minus rho. So the pressure is negative for a cosmological constant just because it's Lorentz invariant. Strange, okay? It means, but it is strange. I mean, the cosmological constant is a weird kind of energy with negative pressure. And the negative pressure is forced on you by its Lorentz invariance. There's a simple version of this. This may still seem confusing. Imagine I've got a string in string theory. Okay? Here is a string. Okay? What is negative pressure? Negative pressure for a one-dimensional object is just the tension. Okay? You will remember energy conservation. dE equals minus P dV, right? That in the case of a string, it's particularly easy. The change in energy of the string, imagine I've got a perfect string so that when I pull it some length of fixed tension, okay? So that's what a superstring is. It's an object with fixed tension. So as I pull it out, the energy I get is equal to the tension, let's call it T, times the length, times X, if X is the length. Okay? So how do I account for this energy? Well, the reason I get that energy is because I'm doing work against a tension which is pulling inwards. And that's a negative pressure. The string tension is the negative pressure of the string. And likewise, if I have a two-dimensional membrane, its tension pulls the surface inwards. And that's a negative pressure. And a cosmological constant is really the tension of space. Okay, so you should imagine this cosmological constant pulling space inwards. Now, the paradox in Einstein's equation, you might think that causes the universe to collapse, right? It causes the string to collapse. But the strange thing in the Einstein equations is that if we combine these equations, we'll get an equation for A double dot. Let's add this equation to that equation to get rid of the A dot squared. And we will see, you see, A dot squared plus K is A pi g rho over 3 times A squared. Okay, so this is going to give A double dot, I'll just write the answer, which I know, minus 4 pi g over 3 A times rho plus 3p. Okay, this is called a Ray-Choudhury equation. But basically it says that the acceleration due to matter is not rho. This would be the naive sort of Newtonian result, that the F equals ma, where the force is basically the mass over a squared. But you have p rho plus 3p. Now, for cosmological constant, p is minus rho. This term is negative. A double dot is positive. So negative pressure in gravity is repulsive. The cosmological constant causes space to blow up. And that's what seems to be happening to our universe. It's dominated by p equals minus, it's dominated by this stuff. It's 72% of the energy in the universe is in the cosmological constant. And in this equation, the combination here is negative, and A double dot is accelerating. Our universe is expanding faster and faster. Right? It's crazy, but this is reality. Okay? So, and the intuition is very strange, because as I say, it's actually negative pressure causing accelerating expansion. That's why everybody's so confused in physics. What is this stuff? It's bizarre stuff, and it's dominating the universe, right? So it's up to you to understand it. So I better finish there. Any other questions? We'll do some more next time. We'll see how to visualize the general cosmological solution next time. It's not so difficult.